A spacecraft built by humans has flown through the outer atmosphere of the Sun, a place where temperatures can climb into the millions of degrees, a place filled with radiation, magnetic storms, and streams of charged particles. And somehow, it survived.
This is NASA's Parker Solar Probe. It became the first spacecraft to touch the Sun. But that creates one impossible question. If the Sun's corona is millions of degrees hot, why didn't Parker Solar Probe melt? From Earth, the Sun looks calm, a glowing disk in the sky. It gives us light, warmth, seasons, and life. But up close, the Sun is not peaceful. It is a massive ball of plasma, almost 1.4 million kilometers wide, powered by nuclear fusion in its core. Deep inside, hydrogen atoms are crushed together under extreme pressure, releasing energy that slowly works its way outward. Eventually, that energy reaches the visible surface of the Sun, called the photosphere. The photosphere is already incredibly hot, about 5,500 degrees Celsius. But above that surface, something strange happens. Instead of cooling down, the Sun's atmosphere gets hotter, much hotter. The corona, the Sun's outer atmosphere, can reach millions of degrees. That should not make sense. Move away from a campfire and it gets colder. Move away from a heater and the air cools. But on the Sun, the outer atmosphere is hundreds of times hotter than the visible surface below. This is one of the greatest mysteries in solar physics. Scientists call it the coronal heating problem.
And to solve it, NASA had to do something that once sounded impossible. They had to send a spacecraft into the atmosphere of a star.
For most of history, the Sun was untouchable. Ancient civilizations worshipped it. Astronomers studied it. Telescopes revealed sunspots, flares, and violent eruptions.
But no machine could get close enough to enter its atmosphere. The Sun was too hot, too bright, too powerful. Any ordinary spacecraft would be destroyed long before reaching the corona.
But scientists knew that studying the Sun from Earth was not enough. To understand the solar wind, solar storms, and the mystery of the corona, they needed direct measurements. They needed to go there. So, NASA built Parker Solar Probe, a spacecraft designed not to avoid the Sun, but to dive toward it. Launched in 2018, Parker began a dangerous journey through the inner solar system. Its goal was simple to say, but extremely difficult to achieve: touch the Sun. You might think getting to the Sun is easy. After all, the Sun's gravity is enormous. Shouldn't a spacecraft just fall into it? But space does not work that way. Earth is already moving around the Sun at about 107,000 kilometers per hour. Anything launched from Earth carries that sideways motion. So to fall closer to the Sun, Parker had to lose orbital energy. That is extremely hard. Instead of flying straight inward, Parker uses Venus. Again and again, it passes near Venus, using the planet's gravity to reshape its orbit. Each flyby tightens Parker's path around the Sun. Each orbit brings it closer. Closer than Mercury. Closer than any spacecraft before it. Until finally, Parker crossed a boundary scientists had been chasing for decades. It entered the corona. For the first time, humanity had placed a spacecraft inside the atmosphere of a star. When Parker Solar Probe entered the corona, it was not just looking at the Sun anymore. It was inside the Sun's environment. It was flying through solar material. It was measuring particles, magnetic fields, and plasma from inside the outer atmosphere of our star. NASA described this moment as touching the Sun. And the mission did not stop there. Parker kept diving closer. At its closest approaches, the spacecraft comes within only a few million miles of the Sun's surface. At that distance, the Sun no longer looks like a small disk in the sky. It becomes a wall of light, a blazing ocean of plasma, a violent magnetic atmosphere stretching across space. And Parker is just a tiny machine racing through it. At closest approach, it becomes the fastest human-made object ever built, moving at hundreds of thousands of miles per hour. But speed is not the most shocking part. The shocking part is that Parker survives. So why didn't it melt? If the corona can reach millions of degrees, shouldn't Parker's solar probe instantly vaporize? The answer begins with one important idea. Temperature and heat are not the same thing. Temperature tells you how fast particles are moving. Heat tells you how much energy those particles actually transfer into something else. And that difference is everything.
Imagine placing your hand inside a hot oven. The air may be hundreds of degrees, but for a short moment, you can survive. Now imagine placing your hand in boiling water. The water is much cooler than the oven air, but it burns you much faster.
Why? Because water is dense. There are far more molecules hitting your skin and transferring energy into you. Hot air is less dense, so it transfers heat more slowly. The sun's corona works in a similar way. The particles in the corona are moving incredibly fast, which means the temperature is extremely high, but the corona is also extremely thin. There are not many particles there compared with air, water, or solid matter. So even though the temperature is millions of degrees, there are not enough particles hitting Parker to transfer that energy like a normal furnace would. That is the secret. Parker is flying through a place that is incredibly hot, but incredibly empty. The corona has extreme temperature, but low density. And because of that, Parker does not absorb heat the way our instincts expect. But that does not mean the spacecraft is safe. Far from it. Even if the corona is thin, the sunlight near the sun is still brutal. At Parker's closest passes, sunlight is hundreds of times more intense than sunlight at Earth. The spacecraft needed protection. Its most important defense is its heat shield. Officially, it is called the Thermal Protection System. It is about 8 feet wide and only 4.5 inches thick. The shield is made of carbon composite materials with a lightweight carbon foam core between carbon plates. The sun-facing side is coated white to reflect as much sunlight as possible, and the result is astonishing. The front of the shield can reach around 2,500 degrees Fahrenheit. But behind the shield, the spacecraft's instruments can remain near room temperature. Think about that. One side faces the sun. The other side protects delicate electronics. Only a few inches of material separate survival from destruction. But there is a catch. The shield only works if it is pointed directly at the sun. If Parker turns the wrong way, even slightly, sunlight could hit parts of the spacecraft that were never meant to be exposed. At that distance, a small mistake could be fatal. So Parker cannot just be strong, it has to be smart. Parker's solar probe cannot depend on instant help from Earth. The sun is about 8 light minutes away. That means if something goes wrong, engineers cannot simply take control in real time. By the time a command reaches Parker, it may already be too late. So Parker is built to protect itself. It has autonomous systems that constantly monitor its orientation. Small sensors around the spacecraft detect whether sunlight is hitting areas outside the shield's shadow. If Parker begins to drift, it corrects itself automatically. It keeps the shield facing the sun. It keeps the instruments hidden. It keeps itself alive. This is one of the most extreme engineering challenges ever attempted, because Parker is not flying through empty, calm space. It is flying through the sun's atmosphere, a place shaped by plasma, radiation, solar wind, and twisted magnetic fields. The sun erupts. It flares, it launches storms into space, and Parker has to survive while racing through that environment faster than any spacecraft in history. Parker's solar probe was not sent to the sun just to make history. It was sent to answer questions that affect Earth. Why is the corona so hot? How does the solar wind accelerate? Where do dangerous solar particles come from? These questions matter because the sun does not only shine, it reaches across the solar system. The solar wind is a stream of charged particles constantly flowing away from the sun. Earth is always inside that stream.
Most of the time, our magnetic field protects us. But when the sun erupts, it can send powerful solar storms toward Earth.
These storms can create beautiful auroras near the poles, but they can also disrupt satellites, radio signals, GPS systems, and even power grids. Our modern civilization depends on technology in space, and that technology depends on understanding the sun. So Parker is not only exploring a star, it is helping us prepare for space weather. It is measuring the solar wind close to where it is born, before it spreads across millions of miles. It is giving scientists data they could never get from Earth. And Parker has already found surprises. One of the strangest discoveries is something called switchbacks. These are sudden reversals in the sun's magnetic field. Imagine magnetic field lines flowing outward from the sun. Then suddenly one bends backward like a whip before snapping forward again. Before Parker, scientists knew switchbacks existed, but Parker found that close to the sun, they are far more common and intense than expected. These strange magnetic zigzags may help explain how the solar wind gains speed. They may also reveal how energy moves through the corona. Parker has shown that the region near the sun is not smooth. It is chaotic, structured, violent, alive with magnetic motion. And every time Parker dives closer, it brings back more clues. Clues about plasma, clues about solar storms, clues about why the corona burns so much hotter than the surface below. The most incredible part of Parker's solar probe is not only that it touched the sun, it is that it changed what impossible means. For centuries, the sun was the ultimate boundary, a star too powerful to approach, a source of light and life that we could only study from far away. But now, a machine built by human hands has flown through its atmosphere. It has crossed into million-degree plasma. It has raced through magnetic storms. It has survived near a star. And it did not melt. Because the sun's corona is not just about temperature, it is about density, heat transfer, magnetism, plasma, and engineering pushed to the edge. Parker's solar probe reminds us that the universe does not always behave the way our instincts expect. A place can be millions of degrees and still not burn like a furnace. A spacecraft can fly through the atmosphere of a star and live to send data home. And sometimes, the only way to understand the sun is to touch it. This is infinite science, and the closer we get to the sun, the more mysterious it becomes.